Hi Pre-Calc kids, it's time for another online lesson. This is the last lesson in Chapter 2, something called linear programming. Ties in pretty nicely with 2.6, except here we have a practical application of it. And this is going to be what on the right side your little project is going to be all about as well. So with linear programming, as you can see, our goal is to optimize a certain condition, and that condition might be trying to make the most profit or the least cost of something of that nature. And you're going to have to do that while given certain constraints, and those are limitations that you have. So very practical types of problems here. The problems we do, of course, are simplified, but you'll certainly be able to see the kernel of truth in each and every one of them. And we're going to be using principles from the last lesson, namely graphing inequalities, and then that vertex theorem that will guide us through this particular lesson. So today we're just going to look at one example actually, and we'll be trying some others, of course, in class, and the project that you do will be helpful in this stuff as well. Alright, so here we have a pretty real-life example here. Let you kind of read through it. The idea is there's been an earthquake. We're trying to send some aid to help these people with the earthquake. And just some key things to note here. We're going to try sending bottled water and medical kit. So for the bottled water, every case will serve 10 people. Every medical kit will aid 6 people. And we have some limitations as well. The plane is limited to 80,000 pounds. And we have some weights for the water and the med kits. And the volume, of course, has to be a limiting factor as well, 6,000 cubic feet. So first of all, what we want to look at is my optimization function. And that optimization function is oftentimes maybe a profit or a cost that we're trying to maximize or minimize. Here we're trying to help as many people as we can. So as you can see, the water will serve 10 people, and the medical kit will aid 6 people. So we're going to try to have some optimization from that. I'm just going to write out a little equation here, and you'll be able to see where it comes from. So z is going to be 10x plus 6y. In other words, for every bottle of water we can help 10 people. For every medical kit we can help 6. We're going to try to optimize or maximize that function as we go along here. Chart to help us out here with the rest of this. These are the limitations we have. So what we're going to do is try to make some constraint inequalities here based on that. First of all, let's look at the weight. We see that our bottled water, a case of that is 20 pounds, and the medical kit's a case of that is 10 pounds. So here's what our little constraint inequality is going to be here. Notice that we've let our bottled water be represented by x and our medical kit by y. So see if this makes sense. For my weight, I'm going to use this inequality. 20x plus 10y is less than or equal to 80,000. 80,000 total pounds that the plane has room to carry things, and each case of bottled water 20, each medical kit is 10, 20x plus 10y. It has to be less than or equal to because that's what the plane has. And let's take a look at the volume. Notice it says, the problem says that each case of bottled water, each medical kit takes up 1 cubic foot. So my inequality there is going to be x, 1x, or just x plus y, less than or equal to 6,000. That's what the plane has in terms of volume. Now what I'm going to do is graph each of these constraints, and I'm going to try to set up a little intercept chart here, and then we're going to be doing some graphing and solving on the next slide. So as you can see, we've done a little of this before in graphing. Most of the time we've used the slope-intercept method or something like that to graph. But do you see that in this case, if we pretend that this is an equation, if x were 6,000, then y would have to be 0. and vice versa. If y was 6,000, apologize for not much room there, that would be 0. So those are a couple of the points I'm going to plot on my next slide here, which is the graph. Then going back to my weight, if I make one of those charts here, an x and y chart, you'll be able to see that if x were 0, well, 20 times 0 is 0. That means 10 times 8,000 would be 80,000. And vice versa, once again, if I put a 0 in for y, 20 times 4,000 will give me that. So that gives me a couple of ordered pairs, a couple of intercepts actually, that I'll be able to plot on my next graph here. In graphing those two things, by the way, on my graph that I have here, these are going to be in thousands. These are going to be in thousands. So the first thing I think I'll graph are the bottled water ones from last time. And if you remember, the 2 points were 0, 8 for 8,000 and 4,000, 0. So right like that. Again, these are all in thousands. I am going to draw a line between them. Don't laugh at my line. I do not have a straight edge here. Not too bad for an old geezer, I guess. And if I was going to do some shading here, I would actually be shading this to the left. Remember, these are all shaded problems because of the inequality factor. So then I'm going to graph my other one, and that was the medical kits, I think. And if you remember, those ordered pairs were 0, 6,000 and 6,000, 0. So that's going to look like that. Again, my line here is going to be sneaking through about like that. And if I was going to do shading, again, it would be shaded to the left like that. Now, my overall shading then, where both of these, the intersection of these shadings, then I think you can see will be this region. Looking like that. So that's the intersection of my shadings. Now, as you remember from last lesson, perhaps, what I want to do is I want to look at the vertex points. Those would be the points I'm going to check. So as you can see, I have one up here, one here, one here. I also have one at 0, 0, but I'm not going to check that one because that doesn't really make too much sense in this case. So I go back to my optimization equation, which, if you remember, was 10x plus 6y equals z. Again, this is trying to tell me how many people I can help or what I can help the most. I'm going to look at my ordered pairs, and the ordered pairs I'm going to look at are 0, 6,000. That's that point right there. And let's see, so I'm just going to write it out like this, I guess, 0, 6,000. My middle point here, even though you can't see it really well, is supposed to be the point 2,000 and 4,000 is what it's supposed to be. Doesn't look too much like that. And my last one here on the x-axis is going to be 4,000 and 0. I need to check each of these because I know that from that vertex theorem that one of these 3 points is going to give me my maximum value, and that's what I want. So just substituting these points, these values in for x and y was 0, 6,000. I'm going to end up with, I'm going to get a different color here for emphasis. I'm going to end up with helping 36,000 people with a 2,000, 4,000 point. Again, I put 2,000 in for x, 4,000 for y. You can check this. I'm just kind of rushing through this a bit. That's going to help 44,000 people. And lastly, the 4,001, that's going to help 40,000 people. So the answer then, how many bottles of water, how many medical kits do I want? We have maximized that, so the one that's going to give me the most then is this option right here. And so that's going to be 2,000 bottles of water and 4,000 of that med kit. Now, each of you is going to get a problem similar to this that you're going to do as part of the project on the right side. These are kind of interesting, and certainly there's a decent dose of reality in these as well. So thus ends our little linear programming lesson, and we'll talk about it more in class. See you then. Bye now.